And okay, let's come back to our class, nonlinear optics. Last week, we introduced kind of the most basic nonlinear process as a second harmonic generation, where you have a frequency omega light input into a piece of dielectric, and then you can output two omega components as the second harmonic. And then we talk about, okay, the corresponding physics process is that you have two photons at the fundamental frequency being consumed, and then it's being converted into one photon that has twice the frequency. So in this process, because you consume two lower frequency photons and generate one higher frequency photon, so the overall energy conservation is satisfied. And then we go into details and then write down the coupled equation for fundamental frequency and then harmonic frequency, and then we check the energy conservation. Okay, and also what we do is that we figure out that phase matching condition, that's a term of e to the I 2k1 minus k2z. Okay, this term is very important in terms of how much power, how much second harmonic power you can get from this dielectric material. And also, if you just by looking at this form, you know that okay, this is correspond to momentum conservation because momentum is h bar k. Okay, so whenever you satisfy phase matching condition, you maximize the conversion efficiency, okay, from fundamental frequency to second harmonic generation. What the condition that you actually are matching to is first energy conservation, and second is momentum conservation. It makes a lot of sense. And we also derive the final equation that tells you the output power versus all the parameters in the system. And then we can see that the output power, okay, increase with the decrease of mode area, optical mode area, and that's the reason why we're going into integrated photonics, okay, to have micrometer scale waveguide in comparison to millimeter scale free space laser beam. And then the power is actually the harmonic power is proportional to the square of the input fundamental frequency power, right? So this is a typical nonlinear behavior, right? The output doesn't depend linearly on the input. And also we know that okay, if you want to have higher output power, what you also want to do is that you want to have the refraction index almost the same. While the refraction index difference between the fundamental frequency and the harmonic frequency, you want this difference to be as small as possible, which is the same as momentum conservation and phase matching condition. Okay, and then there's one very obvious one is that you want to have this you want to have this chi2, the nonlinear coefficient, as large as possible, because this actually generates the entire nonlinear process. Okay, so one thing that we haven't really talked about here is that we covered the first three, and then we kind of say, okay, the fourth one is just a search for material, right? And then you can go online, you can do that. But one thing we haven't really talked about is that what type of material actually has non-zero chi2. Okay, so what type of material actually has non-zero chi2? Okay, and just think about the everyday experience, right? So if you shine a laser light onto a piece of glass or into the water, right? It doesn't generate second harmonic light, right? You don't see a red laser beam converted into ultraviolet. And I don't know if any one of you have fiber internet in your home. Fiber internet, the laser light is at 1550 nanometer. Okay, if you plug that out, and then you point that into whatever dielectric material you have, that doesn't convert into a red light. Okay, so what it really is that there's some condition. There are actually some condition for non-zero for any material to achieve non-zero chi2. Okay, actually most of the material has zero chi2, like water, like glass. That's why we don't see second harmonic easily. Okay, so so here today we're going to first quickly kind of explain to you guys, okay, what's the reason, or how you can analyze whether a material has a non-zero chi2 or not, right? Otherwise, like if you want to do experiment and then you're optimizing all this parameter and then eventually you find out, okay, the chi2 is 0, so that's why you never see any signal. So the key word here is something called is symmetry. Okay, it's actually inverse symmetry of the material. Okay, now the argument is like this. Okay, let's take a look at the nonlinear polarization. Okay, so this is a nonlinear polarization expression, and the thing that you want to do is that you want the, well, if you want to generate a second harmonic generation, a second harmonic line, of course you want the nonlinear polarization to be non-zero, right? To be non-zero, and then according to this equation, then this has to be non-zero, this too has to be non-zero. Now let's take a look at this expression. And then the very first thing, okay, if you're, let's say if you're from, Department of Math, okay, so something you would notice immediately is that this expression, okay, this expression has different parity on the left-hand side and right-hand side, okay. What do I mean by that parity? Suppose you have a material, dielectric material, okay, and then I appoint a coordinate to it, x, okay, x, y, z. Appoint a coordinate to it, right? This direction is z, this direction is x, and then the direction going out of the whiteboard is y. Okay. Now, let's assume, okay, let's assume that the material here is isotropic. Okay, isotropic material, which means that the material is the same no matter which angle you look at it. Right? That's the most common thing in nature. Right? Like water, glass, they're all isotropic. And isotropic doesn't mean that isotropic is a concept, statistic concept. It doesn't mean that if you look at x direction and z direction, it doesn't mean that when you look at, for example, a piece of glass, it doesn't mean that the atom arrangement is exactly the same. It doesn't mean that. What it means is that it's more like it's the randomness, okay, because you're not a crystal structure, for example, the glass. So there's a randomness in each direction, okay? And then the randomness is actually the same, right? So the way to kind of draw the analysis is that you can think about it as that now you have two streams of random number, right? If you really compare these two streams of random number, they're not the same, right? Compare number by number, number by number, they're not the same. However, if you calculate their average value, calculate their deviation, calculate all kind of statistics, they're indistinguishable. Okay, so that's what we mean by isotropic. Okay, so if you look at it as a statistic ensemble, okay, then they're the same. But if you go into a microscopic scale, look at individual atoms, okay, then they're not. So now, when we say isotropic material, okay, and then we say, okay, they're the same from every direction, then what we typically mean is that, what that typically means to us is that the material parameters, for example, chi, and refraction index, and well, some others like Young's module, okay, all this, they're the same regardless of how you assign your coordinate, right? Or the other way to say is that if you shine your light going into the media this way or this way, you're going to see the same coefficient, right? That's the meaning of isotropic. If it's not, then you're going to, okay, you can say, okay, this direction, the refraction index is larger, so I can assign, I can say this direction is different from that direction, okay? So now if you look at this, okay, then you say, okay, this is material property, it's not going to change if I flip the coordinate or if I do any change to the coordinate. Then you start to see the parity problem here, okay? On the left-hand side, it's one vector. Okay, one vector. On the right-hand side is two vector. Okay, two vector. Then what will happen is that, okay, in this, let's say P is in this direction, and also E is in the same direction. Now, in this coordinate, both P and E, they are pointing towards the positive direction of X, right? So we can say that, okay, P, let's say this is X. Okay, and then we assign the coefficient plus, meaning that, okay, we're using this coordinate. This is a plus coordinate. Now think about it. If we reverse the coordinate, okay. Let's see. Yes, okay. So if we say, okay, pointing downwards is X, okay, and Z is the same. You just, kind of what you do is you rotate the coordinate by 180 degrees, right? Then, should we see any difference should we see any difference in the material coefficient? No, right? Because this is isotropic, so no matter how you put it, how you rotate it, it's always the same material. But then, what about the polarization and then the electrical field in this coordinate, right? So in this coordinate, what you would see is that your nonlinear coefficient, nonlinear polarization, will add a minus sign in the front, right? Because previously you're pointing upwards. Now in this coordinate, pointing outwards actually meaning pointing towards a negative direction, okay? And the same apply to electrical field, actually apply to any vector along this x direction. In this minus coordinate, okay, pointing upwards meaning minus, right? So now if you plug this, back into here, then, well, now think about it, because it's isotropic media, right? So what we're assuming is that whatever physics phenomenon you see in an isotropic media doesn't really depend on how you assign the coordinate, or doesn't depend on how you position your media. Okay. So then what you will get is that this is in plus media, this is in plus coordinate, this is in minus coordinate. Is that, okay, you have minus P and L, that's your polarization. It should equal to, okay, minus. Right, it should follow the same, exactly same equation, okay, just everything described in the minus coordinate, okay, exact same equation form, and then in the minus coordinate. So that means, okay, P and L polarization goes to minus, electric field goes to minus, electric field goes to minus. Now if you kind of cancel out all the minus sign here, then what you will see is that you will see P and L here equal to minus okay, and this actually makes sense, right? Because this equation, left-hand side is a vector, right-hand side is vector squared, right? So if you add a minus sign in your coordinate, the left-hand side will have to flip, right, from positive to minus to negative, and then the right-hand side, because it's vector square, right? So it's actually left unchanged, right? So then, so then now you get two equations that look almost identical, but then they're just off by a minus sign. Okay, this is in this coordinate, this is in this coordinate, and because the material here is isotropic, then what it means is that no matter in which coordinate, its nonlinear coefficient is the same. Right? If you can measure the difference, then the meteor is not isotropic. Okay? So because it's isotropic, what it means is that chi2 in the plus meteor equal to chi, well, in the plus coordinate equal to chi2 in the minus coordinate. Right? What it means is, well, what it means is chi doesn't depend on your coordinate. Okay, so now you can combine these two equations now, right? So this is in your, let's say we assign that to chi. Okay, so this is in your minus pointing downwards coordinate, and then you can also write down the equation of in the pointing upward coordinate. Okay. So you have nonlinear polarization equal to something, and it also equal to the negative of that. Right? Then what is the solution to these two equations? What can be possibly the solution to these two equations? The only solution is the left-hand side and right-hand side has to be 0. Right? Only 0 equal to its minus. Right? So these two combine give you, okay, 0, okay, and then chi has to be 0. And the only way that you can make nonlinear polarization 0 is your chi is 0, right? Because you can always have non-zero electrical field, right? You can input an electrical field, so you cannot guarantee electrical field is 0. Okay, so the only way that you can have the left-hand side and right-hand side both equal to 0 is chi is 0. That means your nonlinear polarization is 0. Okay, so from here, what we can see is that for chi2 process, okay, for chi2 process, and actually for any chi odd number process, okay, for any even number process, right? Second harmonic, fourth harmonic, sixth harmonic, they all have this same problem here, is that the left-hand side has, you can say, has odd parity, the right-hand side has even parity, right? And then they naturally don't match. They can't equal to each other, so that the solution has to be 0. Okay, the chi has to be 0 in isotropic media. Okay, so so when people summarize this, okay, although we use isotropic media as an example, but when people summarize it, you see that the critical part is that you actually inverse the x-axis from upward to downward. Okay, that's the thing that we apply here. So that's what we say inverse symmetry. Is that if your media is the same when you flip it down, okay, from upward to downward, and then your media have the same has the same crystal structure. Okay, has the same crystal structure, which will give you the material parameters. Then we call this media has inverse symmetry. So for inverse symmetry media, for inverse symmetry material, the chi, okay, the second harmonic chi2 or chi even number, okay, they're always 0. They're always 0. So that's why you would never be able to see harmonic generation if you're shining laser to a piece of glass. Right? It just never happened. Okay. Also, you shine a laser into water. Okay. You can actually boil the water, but you still won't see second harmonic generation. Okay. And then there are some rare cases. Okay. If you really do a Google search, you will see. Okay. There are some reports saying that people say, okay, they see second harmonic generation in optical fiber, which is made of glass, right? So how can you explain that? So those situations happens is that there are actually impurity in glass. Okay, if you have impurity in glass, and then those impurities have some structure that's not isotropic, then you violate the inverse symmetry, and then it will give you a non-zero chi2. Okay, so breaking the inverse symmetry is actually the key to generate a non-zero chi2. Okay, and what materials have non-zero? What material doesn't have inverse symmetry? Okay, most crystals doesn't. Okay, most crystals, unless you do like cubic. Okay, even for cubic, there's some way to cubic lattice. Okay, even for cubic lattice, there's some way to generate non-zero chi2 under certain polarization combination. But for example, this is a qubit. Okay, if you just use the qubit crystal, then it also has inverse symmetry, right? For example, you use this as a center, you flip it up and down, this always comes down to here. Okay, so if you shine a piece of laser into a crystal qubit, and then what you're doing is that, okay, your electrical field is in this direction, your polarization is also in this direction, then you will never see any harmonic generation, right? Because it's also inverse symmetry. Okay, it's also inverse symmetry. But if your crystal violate that, okay, if you have meteor that violate the inverse symmetry, then the condition you derive chi2 is 0 no longer holds. Okay, no longer holds, and then you will start to have non-zero chi2. And in the textbook, okay, we assign you the textbook, the quantum electronics or photonic textbook. In the chapter of nonlinear optics, there's a table, okay, telling you that what type of crystal will have what type of chi2. Okay, so there's actually a table you can read into that, and then to extract. Okay, it kind of you can use it as a tool book, and then there you can kind of if you are dealing with this type of crystal, and then you look into that table, and you can see, okay, which components in the chi2 is not 0. Okay, and we're not going into the detail here because if we go into there, then we have to start to talk about crystal structure, and then also crystal symmetry. Okay, with the symmetry group like 422, keep going. Okay, this type of symmetry group, and that would take us one entire class at least. Okay, so takeaway here is that if you want non-zero chi2, if you want second harmonic generation, or if you want any chi2 nonlinearity, you have to break the inverse symmetry in your media. Okay, and that appears in crystal, in certain type of crystal. Okay, any questions here? Okay. We're going to, while there's 45 minutes left in this class, so one thing we're going to do very quickly is to cover another chi-2 nonlinearity effect. Okay, it's called sum frequency. Sum frequency generation. Okay, the reason that we want to do this is that here, okay, previously we're only working with the second harmonic generation, which is the simplest possible case in nonlinear optics, right? One input, one frequency output. Okay, that's the simplest case. So we're looking at a little bit more complicated case, is sum frequency. And sum frequency, well, by its name, you will know that, okay, you must have two input, okay, and the output frequency is a sum of those two input frequency. That's why it's called sum frequency. And for sum frequency, what we're going to do is that we're going to quickly go over this, okay, and then just like a reinforced practice that revisits some of the concept here, and then make sure that all this still apply, other than the apply even if it's not the simplest harmonic generation process. Okay, so sum frequency. Okay. Sum frequency talk about a problem like this. Okay, so if you have an input, if you have two light going into the nonlinear media, of course they will transmit. Okay, can you generate a wave which frequency is omega 1 plus omega 2? Right. You might think, okay, then does this ever happen? I don't know if you guys ever do electronic experiment, but in electronics, there's the coupler, right? The frequency coupler, which actually take in, okay, which actually take in omega 1 and omega 2, and you can do a sum to omega 3. Or more often, the frequency coupler in electronics, what it does is it takes in omega 1 and minus omega 2 and convert it into a DC band, omega 3. Right? So, so sum frequency and different frequency is actually very, very common in electronic experiment. Okay, and in optical domain, sum frequency is actually less common. Okay, but the mathematics, why we talk about sum and then later difference frequencies, because their mathematical behavior is actually different. Okay, so sum frequency and difference frequency, they also happen in optics. Okay, but in optics, difference frequency is much more important, and later we'll tell you guys why. Okay, so let's quickly, go over this. And then this is kind of the you would develop this protocol in your mind. Is that, okay, whenever you are given a piece of problem, okay, then how you're going to solve it. So the first thing you're going to do is that, okay, is to write down the nonlinear polarization, right? It's the same thing. It's chi2 E and E. Right, and then we say that in this class, let's see, I think I miss epsilon sign, yes. So in the note, page 22, the first equation I write down, I think I miss the epsilon sign here. Okay, and second thing, well, and of course, like any other calculation in this class, is that we want to simplify, saying that all the polarization align at the, for example, the x-axis, so that you don't have to worry about the tensor and then all the polarization. So simplification goes to here, chi2 E and E, right? So it's just E squared. So far it's actually the same as second harmonic generation. And the part that will start to be different is that how can we write down the electrical field, right? So right now, so for the electrical field, the field that we care about, okay, is R3, right? You have two input and then one output. Well, two input, of course, they transmit, but also you generate new wave in the nonlinear media. So E1 okay, and then you have E2 and then you have the sound frequency that you generate. And of course, complex conjugate. Okay, and then you will want, because it's sound frequency, so omega 1 plus omega 2 equals to omega 3. Okay, those are the three frequency or three electrical wave components that you care about. And one immediate question you might have is that, okay, we just talk about second harmonic generation. There we have I omega t, and then there's another term is 2I omega t, right? Why can't we ditch that term here? Why can't we ditch that term here? It's the same crystal. It's the same crystal. You still have the E1 input. You just add another E2. But why all of a sudden, that we decided to throw away that term? Okay. There's a mathematical reason. You can say that, okay, you can argue mathematically saying that, okay, we know that there will be harmonic generation, and as long as in non-depletion region it doesn't affect E1, so you don't have to include that. Okay, that's one argument that's valid in a mathematical sense in non-depletion region, but it's actually not the reason why we do that. The reason why we do that later you will start to see is that you can see here is that the phase matching condition, right? You can already imagine when is the most efficient time. Well, say omega 1, omega 2, omega 3. The physics process correspond to some frequency is that you have omega 1 frequency photon and omega 2 frequency photon, and they're absorbed by this by a media, and then emit one photon that's at frequency omega 1 plus omega 2, right? So you can kind of see that if you want this process, some frequency process, to happen very efficiently, then you would have to, well, the phase matching condition would be, you can guess without even calculation, any calculation, is the momentum conservation process, momentum conservation condition, right? It's a K1 plus K2 equals K3, okay? K1 plus K2 equals K3. That's the momentum of these two photons together equals the momentum of the sum photon. And if you kind of plug in, okay, the expression of K, then what you will see is that it will be N1 omega 1 plus N2 omega 2 equal to N3 omega 3. Okay, N3 omega 3. Do you guys still remember what is the phase matching condition for harmonic generation, second harmonic? The second harmonic generation is N omega equals to N2 omega. Okay, N omega equals N2 omega. So if you look at this 2, what you will find is that the phase matching condition for your second harmonic generation is very different from your phase matching condition for some frequency generation. So typically in an experiment, these two will not happen efficiently at the same time. Okay, if your experiment is set to look at some frequency generation, then unless some magical things happen, otherwise you wouldn't see any signal for your second harmonic generation because simply it doesn't phase match. Okay, if you're set to do second harmonic generation in your crystal, then also you will not typically will not see some frequency, okay, because a phase matching condition doesn't match. Okay, so that's the reason why, although we have these two, and then these two as input, and of course you would think, okay, they will have harmonic generation, but because the harmonic generation is very small, there's no phase matching there, so we don't include them, okay, in the calculation. The same will apply to difference frequency generation or any other type of nonlinear process. Is that when you write down some term, you can do some analysis and figure out, okay, do I really need to include those terms here? And this is very important, is because if you don't do those analysis, this is a Taylor expansion. You can include infinite amount of terms, right? So if you don't throw away anything, then this calculation is infinite, and then you can't really get anything useful. Okay, so now let's plug in this E, okay, to this nonlinear polarization, and the reason is, right? The reason is our general nonlinear equation is. Let me see, probably I can write it down here.
Excuse me, the second harmonic generation is a special case of the sum harmonic, is that right?
Yes, when omega 1, omega 2 is the same, yes.
So by the phase matching condition is not the same.
It's actually the same. Let's say if omega 1 and omega 2 is the same, right? Then you have, on the left-hand side, you have n1 omega 1 plus n1 omega 1, right? If you're,
yes.
Okay, so it's 2, right? 2 n1 omega 1 equals to, let's keep it n3. Omega 3 is 2 omega 1, right?
Yes.
Okay, so 2 omega 1. Right, so you cancel 2, cancel omega 1, you get n1 equal to n3. Right, this is exactly what you have here. N omega, yes. Yeah, very good. So yeah, that's some frequency is a special case for harmonic. And that's an important point, is that while there's a difference in electronics and optics, in optics people usually separate them because their phase matching condition, okay, usually doesn't match. But in electronics, people usually don't distinguish these two. Okay, for example, if you buy a coupler, you can see some frequency. You will also, at the same time, you will also see harmonic generation if you put the output into a electrical spectrum analyzer.
Yeah.
So,
and this is the basic principles of the optical modulators and mixers, yeah.
Yes. Modulators. One of the frequency is electrical frequency, right? And then the other is optical, and then the sum is this optical, and then you create a little bit of sideband, this side and also this side, right? One is the sum frequency, the other is the difference frequency. Yeah.
Thank you.
Very good. Okay. So okay, let's come back here. It said the general nonlinear equation is 2ikj. We have seen this many times now, so I will just write it down. Okay, equals to so the left-hand side is always the same, right? Left-hand side, you plug this in, and then how many frequency components you're looking at, then you will get how many terms, on the left-hand side, right? It's just do a differential on this term, and that's it, right? So now the question is the right-hand side. Okay, the right-hand side is complicated. It's because, okay, you have the square term here. Okay, you have the square term here. So your electrical field. Let's don't include the vector. Okay. Your electrical field, you have E1 term, and then I'm dropping all the exponential and the vector. E1 plus E2 plus E3 plus its complex conjugate. Right. When you do the square of this, okay, you can count how many terms you will have. Right, I think it's C62, right? This is how many terms you will have. So it's kind of a practice that I suggest you guys all do at least once, okay, to extract the terms that correspond, well, to kind of separate different terms that correspond to different frequency, to correspond to different physics process, right? And then the very first thing you will see, okay, in this square is that each components, right, will have the square. So you have E1 square, E2 square, E3 square, and then their complex conjugate. Right? E1 complex conjugate square, E2 complex conjugate square, E3 complex conjugate square. And these are the harmonics, right? These are the harmonics. And then we throw them out because normally when we do some frequency generation, they don't phase match, okay? So harmonics. So when you throw them out, you have to kind of be very specific, why are you doing it, okay? And then the second part would be the sum frequency, right? Okay, you have E1, E2. This is what you want, E1, E2. When they multiply together, their exponential would come together, and then you will have omega 1 plus omega 2. That's what generate your second harmonic. That's what generate your sum frequency. And of course, you will know that. Okay, there's a 2 factor here because you can pick up E1 first. You can be E1, E2, and E2, E1, right? There's some redundancy there. Okay. And then what else? What else? You will see, oh, okay, of course, this has its complex conjugate, which is E1 complex conjugate, E2 complex conjugate. Okay. And what else? You will also have E1 times with E3, right? That's a sum frequency that's between omega 1 and omega 3. That can also happen. Okay. But does that matter? Probably doesn't, right? Because when you have E1 plus E3, first E1 plus E3 generate a new frequency, right? That's omega 1 plus omega 1 plus omega 2, right? That's 2 omega 1 plus omega 2. It's a new frequency. That's the first thing. Second is that omega 3 should be actually much smaller than E1 and E2, right? Because E3 is a generated frequency here, okay? The third thing, that's the most important thing here, is that the reason that we throw it away is because the phase matching condition for omega 1 plus omega 3 should be very different from the phase matching condition of omega 1 plus omega 2. Right? Again, there's a different phase matching condition. And in electronics, okay, coupler, this is not the case. In coupler, you will actually see all of them. They will just have different, especially in if you plug in your output to electrical spectrum analyzer, it's log scale, right? You can, even it's like 100 times weaker, you can still see it. Then in electrical coupler, then you will actually see all these terms. Okay, that's where they come from. Here we neglect it. Okay, and also you will have the same idea as E2, E3. That's from omega 2 plus omega 3. Okay, that part also not important in our calculation. Okay. Now then we start to touch the term that so far, okay, if you look at the term, what we're doing is we're having the amplitude, well, we're having E1 times E1, E2, E3, right? We never cross to their complex conjugate. Okay, so those are, you can kind of predict, okay, there will be the same amount of terms, okay, created by this process. And the very simple one would be, so this one stay here, these two go away, okay, is E1 conjugate, right? This is just a number because the time-dependent terms, okay, the complex number term, okay, they cancel each other. So this is a time-independent term. And time-independent term doesn't matter, it's because your nonlinear polarization has to be time-varying, okay, time-varying, so that you can induce a polarization that create a new wave, right? So anytime you see this, actually they all have a 2 here. This all doesn't matter, okay, because they're not time dependent. They're not time dependent, okay? Now, if we keep going, then you will start to have E1 cross with E2 conjugate. Okay, so what does it represent in terms of physics process? Here you have E minus I omega 1t, E plus I omega 2t. Right, so what it really is E minus I omega 1 minus omega 2t. Okay, so this is a difference frequency generation, come from this term. Okay, come from this term. And you can use the same argument, omega 1 minus omega 2 will generate frequency that's not the same as omega 1, omega 2, omega 3, right? And then the phase matching condition, okay, if there's no surprise, will be very different from the sum frequency. Okay, so these are the phase matching condition argument that you throw away this term. Okay, and then the same apply to E2. Actually, that's it. This is the term that you throw away. Okay, now let's keep looking. The next term is E1 times with E3 complex conjugate, right? Okay. So can you get rid of this as well? Actually, probably no. If you look at it, then what it is I minus I. This is omega 1 minus omega 3 t, right? What is this? Omega 3, okay, if I write it in a different way, I omega 3 minus omega 1 t, right? Omega 3 minus omega 1, omega 3 minus omega 1 is actually omega 2. Okay, so this term will give you back omega 2 frequency. Okay, so this term you has to keep, right? Because it will couple to the left-hand side the omega 2 term, E2 term. Okay, so this term goes away, this term stay, and then, well, you might wonder, okay, but this is a minus omega 2, right? How does it work? It doesn't matter because all these terms you will have their complex conjugate, right? So if if you see a minus omega 2 term, then the reverse is E1 conjugate times E3, okay? That's the complex conjugate of this term. That will give you the plus omega 2 term, okay? And then so, okay, the next one, you can kind of guess. E1, okay, E1 finish, and then E2. E2 times with E1. You can use the same argument here. Okay, this term has to go away because it's it's a difference frequency generation, and also it's just the this is just a complex conjugate of this term. Okay, and then you have E2, E3. Okay, E2, E3 conjugate. And this one, if you look at it, again, under the same idea, minus I, this is E1. E2 has omega 2 with it. Okay. E3 complex conjugate, so I have a minus sign omega 3t. Okay. So it's the same as EI omega 3 minus omega 2. All right, so if you look at it, omega 3 minus omega 2, that's omega 1. Right, that's omega 1. So this term, again, has the frequency components that we're going to calculate, and also this, because it's omega 2, omega 3, and generally omega 1, then the phase matching condition will be the same as the sum frequency. So you have to keep it. Okay, so you have to keep it. And then of course, the complex conjugate. Okay, complex conjugate. It's a little bit messy, but then let's kind of try to summarize it here. Okay, the E squared term. The thing that we keep is E1, E2. Okay, this corresponds to, let's draw it like this. This corresponds to omega 1, omega 2, generate omega 3. Right, this is a term that corresponds to the sum frequency generation. And of course, complex conjugate, we always have complex conjugate, so we leave it at the end. Okay, and then what is other term? Okay, what are the other terms? And I think all this term has 2 here. Whenever these two are different, then you have a 2. It's because you can have E1, E2 conjugate. You can also have E2 conjugate E1. They're the same. Okay, so that's the first term we keep. Another term we keep is this term, right? 2E. Okay. Here I'm going to write it a little differently. Where I'm going to write down its complex conjugate here. Okay. The reason that I keep this, I write down the complex conjugate instead of itself, is because I want to keep all the positive frequency component. Okay, and then throw all the negative frequency into the complex conjugate. Okay, and then same is that I keep this one. Okay, I keep this one. So 2E2 conjugate E3, and then their complex conjugate. Okay, so here E1, E2 actually means E1 means this, E2 means that, E3 means this. Right, so you have to carry its amplitude, also frequency, also phase. Okay, that's what we mean by E1, E2. And then their complex conjugate. Okay, so this corresponds, the physics process is that, okay, what this corresponds is that it's omega 3 minus omega 2 equal to omega 1. Right? Sorry, my mistake. Omega 1. Right? Omega 3 minus omega 1 equal to omega 2. Okay? So what it says is that, okay, if I have omega 3, okay, and then what I would do is I can take 1 omega 1 here, and then I can generate omega 2. Right, so this process is omega 3 subtract omega 1, not absorb omega 3 and omega 1. That would be some frequency. So omega 3 subtract omega 1 give you omega 2. Okay, and the same process here, same idea, omega 3, okay, subtract omega 2 give you omega 1. Okay, so if you look at it, what they really are is a complete Hermitian process. It tells you how you can go from omega 1, omega 2, okay, to omega 3, right? That's a sum frequency. And then how you can reverse this process, right? Reverse means from omega 3, go back to omega 1 and omega 2. Right? So every physics process has its reverse process. Right? That's the very fundamental, the Hermitian part, right, of the a physics process. As long as you don't drag the entropy thing, okay, into your in any closed system, okay, you should have a reverse process. And the reverse process is the part that maintain energy conservation. Okay, maintain energy conservation. If you drop any of this term and you try to verify energy conservation of the coupled equation you get, okay, from this, you will not see it. Okay, you will see you violate energy conservation. Okay. So, any questions so far? Okay, so what we can get here, okay, is we can get a coupled equation. You plug this back into here, and then you carry all these terms, and then of course each frequency component equal to their own frequency component, and then you can write down a coupled equation, which is in page 23 in the notes, and then I will just copy here. So first is the thing that we most care about is E3, right? What is the E3 at the output port? And the form is exactly the same. And E1, E2. And notice here the phase matching term is exactly what we kind of anticipate, right? K1 plus K2 minus K3. It means that the momentum of K1, K2, okay, those two photons, when they add up, has to equal to the momentum of K3. That's when the maximum efficiency happens. Otherwise, you have a phase, okay, flipping around. The same for E2. Okay, and here is E1, E3, E1, e to the I, K3 minus K1 minus K2, okay, correspond to this term. And the third one is So this is a physics process. Well, this is a coupled equation. And and we're not going to prove energy conservation here because it's the same mathematical process. It would just take us too much time. So what would happen is that it will either see this in the homework, and if you don't, then you'll see it in the final exam or midterm exam, right? So you'll be asked to derive the energy conservation when you have this coupled equation. And one thing that I want to emphasize here is that whenever you get a new type of equation using assumption, right? Using assumption, we throw away many terms. Using assumption, when you do that, you have to verify energy conservation. Okay. Now we have 10 more minutes. Let's quickly solve it. And then let's quickly solve it, and then we can kind of move on from here. Oh, well, we can ask a few questions next class when we get the solution here. Okay. So again, if you look at this, the immediate reaction is that I probably don't want to solve it because it's too complicated. So a few assumptions that you want to make here is that, one, okay, since we have already learned from second harmonic generation that, one second. Okay. One thing that we have already learned from second harmonic generation is that for the process to happen efficiently, you want to have the phase matching condition, right? And that's not going to change. That's not going to change here. Okay, so you can assume, since you know how to do it in second harmonic generation, you will figure it out in some frequency generation. So let's just assume that you have figured out how to do phase matching condition, right? And then you can get rid of this term. Okay, you can get rid of this term. And now that's much better, right? Then you don't have a phase term that hanging around there. It's just a three-coupled equation, okay? And another thing that you can probably assume, just like second harmonic generation, if you recall that in second harmonic generation, we assume that the fundamental frequency, its power is much higher than the harmonic frequency, right? There we reduce from two equations into one equation. So here we can actually kind of do the same thing. So we can assume, okay, it depends on what you want to do, right? You can assume E1, E2 both much larger than E3. Then you're reduced to only one equation, and it's exactly the same equation as your second harmonic generation, right? Because these two would be numbers, right? And that's boring. Okay, that's boring. That's not what we're going to do. You can do that in your experiment if that's your experimental condition, but then here we're not going to do that. What we're going to do is that we're going to assume E2 is much, much larger than E1 and E3. Okay, so it's like a weaker condition, right? A weaker condition. We only assume one of them is much larger than E3. Okay, the other one is comparable to E3. Okay, it's a much weaker condition. What it would do is that you can imagine it would knock out this equation, right? Because E2 is much, much larger than E1 and E3, so whatever happened on the right-hand side doesn't affect my left-hand side. So this means you can always assume E2 Z equal to E2 input. Okay, so it's kind of non-depletion regime again, but not on both input, just on one input. Then this way, what you will get is that you will get by the way, if at some point don't hear my sound, just let me know, because my my microphone, wireless microphone, the battery is very low now. Okay. So what you're going to get here is that you can treat E2 as a number, okay, to replace it here and here. You can get rid of this equation because E2 is not going to change, okay, under this assumption. And then you can also get rid of all this, phase terms, because you assume you know how to do a phase matching condition. Then the net result would be E1, and then there's a bunch of coefficient here. Okay, E2. E2 here is just a number, okay? E2 here is just a number times E3. Right, so it's a coupled equation between E1 and E3, right? This is this equation. And you can get the same for E3. Cool. Yeah.
Yeah, we can see everything now.
Yeah, sorry about that. Okay. So, let's see. Yes, it's still recording. Okay, E3 equation is E2. Where's my note? Okay, so you have a coupled equation that's between E1 and E3. Okay, and then all the thing in the front, they're just coefficient. Okay, they're just coefficient. So if you guys are familiar with coupled equation, usually the result are only two. Okay, the way that you solve it is that you take, for example, we're most interested in E3, right? Then you take a second derivative of E3. Well, you take a derivative of Z on this equation, and then you can, and here will be derivative of E1. Then you can plug in this equation to here so that you get equation solely of E3, okay? And the net result of this type of coupled equation is always two cases. Always two cases. One is that you have a sine and cosine oscillation, right? The other one, because the solution, the form is like this. Okay. I drop all the coefficient. Okay. The form is always like this, right? When you take a derivative of this, the left-hand side is second order derivative of E3, okay, and the right-hand side is E3, and then there's some coefficient, okay, and depending on plus and minus, okay, if it's minus, then if it's plus, then this is sine and cosine solution, and if this is minus, then this is an exponential solution, okay. So here. Here what we can do is that we can define, I think I made a mistake in the note, but anyway, okay. We can define this part as K1, this part, okay, as K2, K3, okay, as K3. Okay, we'll have one more minute. So probably I will write down the equation. And then, okay, so if you take second derivative of this one, so it's partial Z E3 equal to I K3 E1, right? And then you have the E1, so you plug it in, equal to minus, because you have two I here, right? I times I minus K1, K3, okay, and then E3. Okay, so this is the equation you get from here, and then you will get exactly the same equation for for E1. Okay. Okay. And in the next class. In the next class, we would solve this equation and then kind of discuss the unique behavior in some frequency generation, and then we'll move on to the difference frequency generation, and then that kind of wrap up all the second order nonlinear effect. Okay, any questions?